Okay, I would like to start with a quick note on this asymptotic expansion issue, which some of you have raised before. And just to tell that you can, this is a common problem, this is a common issue, and there is nothing mysterious about it. As I told you, it's a matter of validity of the perturbation theory. And you can look at this, you Google this term, method of matched asymptotic series. So term is method of, okay, I'm not writing this whole thing, I'll just give you the link. So there is a Wikipedia page on this. It is called method of matched asymptotic series. It tells you that how to use this asymptotic expansion. Whenever there is asymptotic expansion, how can you effectively calculate a solution of a differential equation that is nonlinear. So this idea of asymptotic, this whole idea of perturbation theory are basically techniques of solving nonlinear differential equations, right? And then of course we imported this in a matrix form because we know that differential equations are also like operators in operator equations in matrix. So the idea you will see there that they show that they show a nonlinear equation in that example, and then they show that how do they try to calculate the solution of that equation, and they say that the solution looks something like this. The actual solution looks something like this. Okay? And then they are saying, so then they are introducing a small epsilon. They are making this nonlinear term with a small epsilon, and then they are saying, okay, up to for a given epsilon, the series converges. Right? And the series convergence means that series will follow this thing, and then it will fall off. Then it will deviate from the actual function. Okay? Then they use a smaller epsilon, and the smaller epsilon allows you to go to with further terms, with more terms, and then it will go like this, and then it will fall off. Like it will deviate significantly from the actual solution. And gradually, if you can do this smaller and smaller solution, and then they suggest a method to deal with this is the method of patches that tells you, okay, you use this one epsilon for a given solution up to this, and take that solution as your H naught, and then do again perturbation theory on that, and then you get a solution beyond this point, right? So this is basically some way to go smaller, and so for a go for a better and better epsilon, when you are like, beta means higher epsilon, and getting a function that is closer to the actual solution. Okay? So what happens in our case is that up to this point, so let's say for a given epsilon, my series converges up to a certain order of term, right? So till that order of term, my perturbation theory is valid, and I will closely follow the wave function and energies, which are the actual energies and actual wave function. After that, my solution starts diverging, my perturbation theory breaks down, and my solution starts deviating, right? Whatever I'm getting from perturbation theory starts deviating significantly from the actual solution, because my basic conditions of perturbation theory are getting invalid, right? The level crossings are happening and all those things, right? So this is the idea that why asymptotic expansion, how asymptotic expansion works, and why it is still useful. Okay? And it's a good thing that some of you are dwelling on that, because this problem becomes very serious in QED, and then you will start to think about physical processes, and there are new physical insights coming from there. Okay, right now it's just a method of solution, and that is the regime of validity of this solution. Okay, is this point clear to you, online audience?
Yes, sir.
Okay, it's all clear here? Okay, now yes. I want you to think about another interesting problem, where a simple problem where the perturbation theory breaks down straight away. Okay, so we discussed about this problem, right? That p square by 2m plus, let's say, ax square plus bx to the power 4, right? This was the problem we discussed. Now we know in this potential, I plot this potential for b greater than 0 looks like this, right? And if b is less than 0, then looks like this. Right? So no matter how small the b is, this will be inverted, right? So this problem will have all bound state solution. All solutions will be of this form, like that, right? and this will have plane wave solution, right? Plane wave solution here and here. Now this is a problem. Now the problem is this, that I am expecting my actual psi to be some coefficient psi naught, right? Psi naught 1, sorry, psi naught naught, coefficient psi 1, psi naught 1, coefficient. Actually, I use n. So let me use n2 naught. Right? Now, how can I ever get a solution that is not a bound solution? That's something that goes to infinity, right? By writing it in terms of solutions, which is the solution of the H0, right? H0 solutions are all like this. Right? How can I get this from there? I cannot actually. So the perturbation theory breaks down straight away. Okay, you can get somewhat some answer which is kind of looks correct at the lower order, but there is a fundamental problem in doing perturbation theory in this problem, in this class of scenario, right? So this is a classic example where perturbation theory doesn't work, and you have to use something else, which we'll learn about only one method we'll learn, something else method, one or two, and that is WKB and variational method, and that is another example where perturbation theory is not useful. Okay, make sense to everyone? Online audience?
Yes, sir.
Okay. So perturbation theory is a technique to solve this nonlinear problems, nonlinear in differential equation sense, and non-perturbative in this sense, non-diagonal forms or complicated Hamiltonian problems, which has its limitations, right? Which has a limited range of applicability. But the range is so huge that kind of explained all experiment till probably 1970s, until people starts encountering strong interaction like QCD and all, and in context of condensed matter, it's high TC superconductivity and so on, topological phases and all. Okay, so that's where the people realize, okay, this is not everything, but it's pretty powerful that it explained all, even the whole QED and everything. Okay, so today we'll talk about mainly Zeeman effect and Stark effect, and as I told you last time that hydrogen atom is the solution of hydrogen atom. This is the Hamiltonian of hydrogen atom. As I said, this is the terms which you didn't do earlier, but now we'll deal with them. So this is the Darwin term, which we will not talk about its origin, not now. This is the relativistic correction. This is the LS coupling. These are all fine structure because they give a perturbative correction up to a certain order, same order, which is called fine structure. Higher orders are called hyperfine. So as I told you earlier, that the origin of this term is simply by writing the kinetic energy is m square c to the power 4 plus c square p square minus mc square, and expanding this. So if you expand it, you will leave that I showed last time. So I am not writing it again. Expand it in power series. Okay. So this is the origin of first term. Given that V is much less than C, of course, then only you can do such expansion. V means P is MV, where P is MV. Okay. So now, so what does it do? This reduces the kinetic energy actually. This is a reduction in kinetic energy type term. And the important point is what is coming out as the small parameter of this expansion. If you notice this, so let me write down one more step. So the small parameter of this expansion is, if I take mc square out, I put 1 plus p square by m square c square. So this is what I am expanding, and this term, and the expansion is actually in terms of v by c square. So 1 plus v by c square. Okay, this is an expansion in that. So b by c is my small parameter of this problem. Okay, and b by c is basically this quantity. You can estimate the velocity for a classical hydrogen atom by using electrodynamics. That becomes this, and this is alpha. This quantity is called alpha, that is 1 by 137. So this thing is called the fine structure constant. All the up to a certain order, the perturbation theories are done by this fine structure constant, and it is completely determined by natural constants in this problem. Okay. So what else? Sorry? M is cube. Okay. Did I make some mistake? Yeah, what is the problem? I didn't get it. Oh yeah, this should be cube. Okay. Okay. So this is the small. So this, there is some subtlety. There is some deep physics about this fine structure constant, but just know that I'm not going into the deep physics of this right now, because there are corrections to it using QED and measurements that involve that tells you very precisely what this number is actually. And but the point I wanted to tell, that in entire this atomic physics, atomic and molecular physics, and also in QED, wherever QED is applicable, the perturbation, the parameter which is appears as small parameter everywhere is this quantity. Okay? And you can see how small this quantity is. So that is why perturbation theory is so enormously successful in this class of problems. Okay, and you will find there are problems where these objects, the small parameter that appears is not small. Right? There is no way to make it small, and it is not only small; it's a natural constant. So that is why it is like it's a natural choice of taking this, and this is never going to change in whatever scenario you are. That's why perturbation theory is the correct description, or a good enough description for all problems of that class. Okay, and you will see there are many theories where that is not true, but that I will not discuss here. Okay. Did you take atomic? Do you know about Bohr theory? Do you know classical electronics? Okay, so can you calculate this by balancing centrifugal force and electrocoulomb force? Okay, okay. So now what I will say, okay, so just to show that this RK term, this term, the order of magnitude for this term with respect to the energies of this term is basically of order 10 to the power minus 4 if you put the numbers. Okay, so that's what just tells you that even low order perturbation theory is going to be very good. So this is the kind of estimate that one should have before starting, I mean, launching a full scale perturbation calculation. Okay, so this is the first correction, this is the RK, and let's just estimate the correction because of that. So I want to estimate delta E1 because of RK. Okay. So what I have to do, I have to take the solution of this part, which is the hydrogen atom you have studied in previous semester, that is NLM, and calculate the NLM is basically, I should write NLM 0 because it is the unperturbed problem. So this is my, now this is my H0 and this is my H1. Okay, and naturally I know that it has a epsilon into it, which is this, which is a small epsilon. So HRK, you can also choose to write it manifestly with that epsilon outside, that is also perfectly fine. So this is my first correction, and where this is the solution of the okay. Now you might notice that there is a problem here. Well, I will come to the problem. This is already a degenerate theory, but the only thing that cares about, the only term that is coming in this is p to the power 4. So p to the power 4 is going to depend on this n. Okay, or p to the power 4, that matrix element is going to non-trivially change, or have some non-trivial relation with only the n. So let's see how the calculation goes. So my En is this, minus 1 by n square m e to the power 4 2h cut square. So this is the En. So I'm writing it just at En, but this is ideally it should be written as En0, because we have used the term notation En everywhere before. Okay. So then my delta E1 Rk is minus NLM p to the power 4 NLM 1 by 8 m cube c square. Okay. So all I have to do is calculate this, and there is a simple strategy of calculating this is by noticing. Of course, this you can do it by the hard way, which is taking the derivative form and taking 4 times derivative of this wave function. But the easy way is this. So notice that h is p square by 2m minus p square by r. Okay? H is of this form. Right? Of course, if I am very careful about notations and units, there must be this. If you are in CGS, you have to put the appropriate 4 by epsilon 0. I am just putting the form and assuming everything is packed here. So p square NLM is 2m h naught by e square by r. So today's class I will jump some steps because otherwise it's too messy to do everything. So this is 2m En minus e square by r. Okay. And therefore your this term, sorry, what is not plus?
It's not plus.
Yeah. Why did I write h naught minus? Okay. So what this should get is minus 1 by 2 mc square you should get this, and this thing will become, let me not write the factor again and again. So this thing will become so basically you have to evaluate this quantity. Number times En square minus 2 En e square 1 by r. Actually it should be plus e to the power 4 by 1 by r to the power 4. Okay, 1 by r or 1 by r square. Yeah, 1 by r. So this is what you have to evaluate, right? Now this thing, I'm just writing down the answer and I want you to work it out yourself. This quantity is minus 2 En by e square. Okay. So there is a trick to calculate this kind of quantity. Using this Feynman-Hellman theorem. I want you to try this, how to calculate this. You know this, you know all about calculating expectation values in hydrogen atom. you can always plug and play with your formulas. You just plug your formula and calculate this. But there is a simpler way to calculate this. So try that. Try to figure out how to calculate this. So similarly, you can also calculate that 1 by r to the power 4 and 1 by r square and everything. So I am not writing all the expression, I will just write the answer. So if you write all the corrections, what you will get? Delta E1 RK. You will get minus m by 2 n to the power 4 e to the power 8 by c square h cut to the power 4 n by l plus half minus 3/4. So this is the first correction you will get, and this correction is of the order v square v by c square. Sorry, it's first order. So first order in v by c, which you can, yeah, this is the first order correction, and because the small parameter is v by c. Okay. So no, there is one issue. This is not v by c. This is actually order alpha square. Okay. The first order correction is of the order alpha square. Okay. So up to order alpha square. Okay. It's all clear so far? I have done all the steps except one step, which is how to calculate this kind of quantities. 1 by r or any power of 1 by r. 1 by r square, 1 by r to the power 4 and so on. Okay. So there seems to be some error in the notes. So this is generic caution about all my notes. They are not error free. So there is, yeah, fix those errors. That's all I say. Okay, so now I will go for the next term, that is the LS coupling terms. These are all plug and play type calculations. There is nothing mysterious into it, very simple. Because the formalism is so well defined, there is no room of uncertainty. Just put things and calculate. There is a term for that. It's called shut up and calculate. Okay. So next term is spin orbit coupling. So where does it come from? It comes from the fact that if I have a moving electric charge, that will generate some magnetic field, and the magnetic field is given by and this is a Coulomb charge, so the field is given by r. So it is 1 by r square, so I am just writing it as r by r. Okay, so the idea is nothing but this, that I have a nucleus around which, like, I am just drawing it as a 2D. So there is some electron is moving at a velocity. So this is generating a moving electric field that is generating a magnetic field, a moving point charge, to be more sure. Let's not say it's moving electric field. But the point is it's a source of electric field. That's why you have this formula. And from the electron point of view, it is basically, so the electron has a mu s, which is because of its own spin, and then it will because of this moving nucleus around it. From electron's point of view, the nucleus is moving around it, right? So that will generate a mu L, right? This is a magnetic field. The mu L is basically a magnetic field that is generated by the moving electron, right? So then in this magnetic field, the Hamiltonian should be written as some mu dot S, right? mu S dot B, where this B is because of that moving electron, right? Or moving nucleus, if I look at it from the point of view of the electron, right? So this term, so this H is basically, so let me just write it as mu minus
Sir,
mu. Yes.
can you explain this second figure that you made by electron point of view once again?
Can you say that loudly once more?
Yeah, I'm saying that the second figure that you made from electrons
Yes.
point of view. Can you explain that once again?
Yeah, so from the electron's point of view, the nucleus is moving around it, right? So the electron will see a magnetic field, this magnetic field that is created because of the moving nucleus, and which is in alternate words, it's basically the electron that is moving around the nucleus, because in our picture we have assumed the nucleus is frozen. That is not true though, nucleus is not frozen, but this is an approximation. It's called Born-Oppenheimer approximation, but this is just an approximation. So then from electron's point of view, the electron is frozen and the nucleus is moving around it, and it will generate this same magnetic field, which is because of the electron's motion, and that magnetic field will generate a magnetic moment, right? Sorry, that magnetic field will couple with this, right? Will couple with this magnetic moment, which is because of the spin. So here I am writing down that coupling, right? This is an effective magnetic field, not applied externally, right? In previous semester you have learned this, right? If I turn on a magnetic field externally, and there is a spin is there, and I turn on a magnetic field, so then there will be a coupling, right? This coupling is this. That was the Stern-Gerlach experiment and all those things, right? So now this magnetic field is coming because of the motion of electron around the nucleus, right? Did you get that?
Yes, sir.
Okay, so this is called internal magnetic field. That is not an externally applied field. And this is the origin of LS coupling. And that LS coupling is basically the sitting at the heart of a large amount of phenomena in almost everything in chemistry, and a huge amount of thing in condensed matter physics and elsewhere also, right? You have learned about LS coupling thoroughly in chemistry in many different contexts, I believe. Many structure, many properties are because of this LS coupling.
And mu s and mu l are the magnetic moments with respect to spin and.
Yeah, mu is the magnetic moment of the electron.
Okay, sir.
The spin magnetic moment. I will write it
Yes,
as
sir.
a
Yes, sir.
moment, right? So if you want, I can write it in mu s. So E by C mu s dot V cross R by R cube. So I am just replacing this here, and this is E by MC R cube. Actually, if I go to the full S description, M square C square R cube E square L dot S. Okay, it's a dot product. I just shift the order. So this V cross R is L, right? This is the angular momentum. So this is L dot S. Right? So this is why it is called LS coupling, or the angular momentum and spin moment coupling. Okay. Now what is important is that you have to calculate this term, right? Because you have to calculate the perturbation for this. So that means you have to know what is this, right? Because this is the correction. If I say this is my H naught, you can say this term is present because you already know what happens when this term is present, or you can assume this term is not there for some reason. And just so, although this is again, one have to be careful about this point, is very important. For the sake of calculation, I am just saying assume this term is not there. But actually you cannot throw that term away if you have to take this term, and vice versa. Why? Because they are same order. This is the same order business that I told you in the first class. It is a controlled approximation. If you are keeping one term of a given order and throwing away another term of the same order, then you are making a mistake, and then you are definitely not going to get the features. But just for the sake of the calculation, I am just telling you. So let us say I just take at the first order, which is where the eigenstates are still n naught for h naught. So I just want to calculate this quantity. Okay. Again, I want you to try. It is worked out in the Shankar's book, and it is by the same method that I wanted you to try how to calculate these things, and you should be able to, because you know all this kind of expectation value calculation from quantum mechanics 1. Okay, so you should get e to the power 6 by h cut to the power 6 1 by n cube l plus 1 l plus half. This is what you get if you do this calculation. Okay, and this is very simple if you just recall. So what? So this result will be useful to calculate the first correction. So let's calculate the first correction. So you can show the delta E. Okay, so I have called this term as E2 in my note, and I think I called it E2 because this is a term of the order alpha square. There is no term of order alpha. So this term I want to calculate now. So one more thing to notice, I want to calculate this NLM HSO NLM. But as we learned earlier, I have a freedom to choose the basis, right? I need not be working with the LM basis. I have a freedom to choose whether I will work in this basis or this basis. In addition of angular momentum, you learned that, right? Right? I can work in any of these two bases. But it turns out that this kind of terms, so for example, J square is L plus A square, is basically L square plus A square plus 2 S dot L. So basically, if I write my L dot S, it is basically J square minus L square minus A square by 2. Right? So you can clearly see it is much better to work in this basis. Right? It is already going to be diagonal in that basis. So instead of this basis, I am going to use that basis. So that becomes, I rewrite this as NJL SMJ, and this is basically NJL SMJ. Okay. And now it is a trivial calculation because it is just diagonal. So then my delta E2 is E square by 4m square c square, which comes from these p factors, and times this, right? What did I miss? Yeah. What should be there? What should we write here? First term. Online audience. This expectation value I want to calculate, right? L dot S in this basis. So what should be the first term? L dot S is this. Sorry, loud? Yeah. So it will be just J into J plus 1 minus A into L plus 1 S into S plus 1. It's very trivial. It's absolutely trivial because of writing it in this basis. Then what is remaining? 1 by R cube. Right? 1 by R cube, we already know how to do that. It is this. So if I plug everything, I get if I plug everything, I get the following answer. As I warned you earlier, this is going to be messy. So I will write a shorter form, alpha square by, no, the shorter form, yeah, alpha square by n square and I get 1 by L into, sorry, L plus 1 to L plus 1 if j equal to L plus half, and minus 1 by L into 2L plus 1 if j is L minus half. There is some other ways to write it also. For example, if I want, I can also write it in terms of j. So alternatively, I can write it as En alpha square by n square n by j plus half to j. J is L plus half minus n by j plus half into j plus half. J is L minus half. Okay. These are like whatever form you want to write it, you can write. Okay. Now I put these two corrections. Yeah, now I remember why did I put E2? Not because alpha square. I put it because alpha square is of course true, but that term was alpha square. I called it correction for this, and E1 is correction for this. Okay, so that might be a little confusing notation because earlier we thought E1 means first order, E2 means second order. So if you want, I can also change my notation by calling it ESO. Okay. So now if I plug everything together, I will get the following answer. So my delta E, because of delta E RK plus delta E SO. We have worked out the two forms and they will together become, after all this long calculation, the answer is very neat. In terms of J, it becomes this. Okay. So your original result was this, that E0, and on top of that you get this correction. Now what does that mean? It means there is a splitting, right? Because now you can say, okay, let's say my levels are this, 1s, 2s, 2p, 3s, 3p, 3d. So I think we should write small letter. Okay. Now I can express this in terms of their j values, and I will see that each of them are splitted like. One more thing to notice, that the energies are always going down. So this is basically 1 is half. Okay. This will split into two parts because of the two j values. One is 2p3 half, another is 2s1 half, 2p1 half. Are you familiar with, by any chance, with these notations? You are familiar, right? Okay, very good. So this is nothing but just to write. This thing is basically j equal to half, L equal to 1, and this is j equal to half, L equal to 0. This is basically j equal to 3 by 2, L equal to 1. So similarly, these will split into three levels. I'm not drawing it all here, it's all there in my notes. Okay. So this simply means that earlier your energy level was specified only by n, right? So they are highly degenerate because of all the L and M values. Now that degeneracy is broken because of this correction, and how it is broken? It is broken in terms of their J values. What is J? J is the total L plus S. Right? So that total angular one is conserved because of the LS coupling. Okay? L and S are individually not conserved. That's why it's best to write it in terms of this. Okay? Online audience? Okay, so
Yes, sir.
if I include this Darwin term, there will be a similar effect, but I am skipping that discussion. Okay, so these three things together, they are all called fine structure. Fine structure constant, because the lowest order correction is up to order this. You will see when the lowest order correction is higher, then will be called hyperfine and so on. Right? Okay. Now, what we'll do, we'll now talk about Stark effect and Zeeman effect. Okay. Now, I had done already this discussion about all this experimental aspects of this, but so let's just straight away go to the calculation. Okay. Okay, I hope everything is all clear. If don't get lost or bothered by the length of calculations or complexity of notation, it's all very simple. It's just it just looks complicated. There's nothing, the difficulty level is nothing compared to what you faced in first 1 month of quantum mechanics 1, or what you faced while studying entanglement or second quantization and so on. It's just calculation. There are certain tricks here and there how to make it easy, but that is best learned by practicing, not by listening. And it's useful, actually, very important that you learn, you do this calculation at least one in your own hand, because prototype of this calculation will appear here and there all the time, okay, if you stick to anything that has anything to do with quantum mechanics. Okay, so now we'll talk about first Stark effect. Stark effect and Zeeman effect, but first we will talk about Stark effect. And as I told you earlier, this was basically kind of observations that people made. So let's say they are looking this spectral signature. They saw two lines in some spectral signature and found if they turn on its electric field, these lines become two, right? 2 or 3, whatever. Okay? This kind of splitting. And the splitting is dependent on in a certain way. Like let's say they can also calculate. These are pretty precise. Atomic physics, like spectroscopy in atomic physics was one of the probably first precision science, where people can measure things of the order of nanometer, angstrom, and be very precise about it, and very like accurate about all these tiniest of tiniest changes. So there were, like, technically this was the most advanced precision science like of that time, and even now, I mean, it's one of the most precision. As I said, that quantum mechanics is verified up to 16 place after decimal, but you might calculate 16 place after decimal in your computer, but how can a measurement device give you? So you can imagine what kind of precision you need. And you know, nowadays interferometry is a gravity wave, the kind of interferometry, the kind of precision it requires for gravity wave is unbelievable. Okay, so these kind of small shifts were observed, and not only that, people have observed, documented this, that they are proportional to square of electric field, or linear to electric field, or magnetic field, and so on. So, right? So those experiments, and as I told you earlier, from 1895 to 1925, all these experiments didn't have a satisfactory explanation. Okay, people first understood why discrete lines, but why this shift because of electric field and magnetic field. That means something is wrong in your theory, or whatever theory you have is not able to explain that. So then it was immensely satisfactory that when 1927 to 29, around that period, perturbation theory was developed, and they could precisely tell that where you should see the line if you turn on this much magnetic field, this much electric field. Okay, so this is what we learn, and there are, as known that all these things were Nobel Prize, each of these experiments, and theory, of course, also Nobel Prize, and they have a lot of use, right? They have a lot of use in various kind of practical applications. One is this NMR, USR, and all kind of MRI also. Okay, so I will not go on talking about all this, but let's just go to look at the calculations. Okay, so let's simplify the problem as usual. So for time being, I am ignoring the relativistic correction, although technically I should not be doing it because they are of same order, but it's just for sake of complexity. So this is, so let's say I have a atom in electric field, and I turn on a magnetic field. Sorry, turn on an electric field, right? So this will be the coupling, for the electric field. So this is my H naught, the hydrogen atom, and this is my perturbation. Okay. So we'll see how to solve that, and let's, for the sake of ease, let's just make it electric field in the z direction. Any direction can be chosen z direction because it's a spherically symmetric system, right? So it's pointed in one particular direction. Okay, now let's also assume that the electric field is so strong that the fine structure is negligible. Okay, so then I can just say, okay, whatever terms I have neglected, they are justified to be neglected because the electric field is so strong, those terms are too tiny compared to that. Okay, so then I have a justification of using this language. Okay, so now one more point I want to mention. So this problem doesn't actually require perturbation theory to solve, because it turns out if you use this something called parabolic coordinate, which is a very strange coordinate, okay, very peculiar, very non-trivial, then you can bring this problem, because this problem has a cylindrical symmetry, right? You have turned on the magnetic field at a particular direction, and it turns out that you exploit that symmetry and go to some parabolic coordinate, and then you can write the problem in a form that becomes an exact, everything becomes exact. But what we'll do, we'll still use the perturbation theory, because going to that coordinate is not very easy. Like it has its own complexity. Calculation has its own complexity. Okay, so let's calculate the first correction. The first correction is this. So this term, so R. Now I will write down the general form, and then I will exploit the point that we have this cylindrical geometry and all that. So what we will use? We will use spherical harmonics. E d3r square. Okay, so we know that this has this symmetry. If I replace r by minus r, nothing changes. Well, no, not nothing changes. We just pick up a, yeah, nothing changes because this minus minus cancels, and what you get is, no, this doesn't cancel. No, this will not cancel. This is a volume element. Yeah, how can it cancel? So if you replace r by minus r, you can show this is an even function. So what you just get is minus okay. So if this is equal to its own minus, so the only way this can happen if E1 is 0, if it itself is 0. Okay. So the first order correction is 0, but notice that this is only applicable, this calculation is only true for the level 100, obviously, because it's a formula of non-degenerate perturbation theory, and this is the only non-degenerate, this is the only non-degenerate level in this problem. So the first order correction, so this is called linear Stark effect. Linear Stark is first order correction in electric field. So that is 0 for the ground state. Okay. So now let's see what happens to the excited state. Now we cannot use the same formula. We have to do non-degenerate perturbation theory. Okay. So let's do it for, now there are second state, there are 4 levels which are forming this non-degenerate space. All this has same, because if it is 2, this can go from, this can be 1, and if it is 1, it can be 1 0 minus 1, 0 and 1. Right? Everybody remembers those things, right? Online audience, do you remember that why there should be only 4 states if at n equal to 2?
Yes, sir.
Okay. So now what I have to do, I have to solve the secular equation. So let's solve this circular equation, which is 200 H1 200 minus E1. So then 200 H1 211 200 H1 210 200 H1 21 minus 1. I have to solve this, right? So similarly, fill this up. There will be this term 211 H1 211 minus E1 and so on. Right? 4 by 4 matrix I have to diagonalize, and what will I get? Okay, before I diagonalize, let's just see something about this. Of course, before I diagonalize, I have to calculate these matrix elements, right? So I have to calculate this quantity, for example. So in general, I have to calculate this quantity. So first thing, notice that all in the first order we have shown this quantity is going to vanish, right? So that means all these terms are going to vanish, right? Any NLM with itself, our expectation value is going to vanish. So all these diagonal terms are vanishing. Got it? Online audience?
So can you repeat once?
So you understood this, that why this is going to 0?
Yes, sir.
Okay. So you understand this term is basically this, right? Because H1 is this E dot R. So this term is basically 200 200, right? This one is 211 211. So this is going to be 0. This is going to be 0. So 210. Oh, I should have written, yeah, 210 H1 210 minus E1 21 minus 1.
Sir,
21 minus 1. So all these terms are 0. All the diagonals are 0, right? So the
sir,
only place, yeah,
can you write a little bit bigger on this matrix part is not visible properly.
okay. Yeah, okay. I am not writing all the matrix element. Just notice that this matrix has all these diagonal entries 0. Okay. By the way, you should take. I am a little skeptical about this clarity issue. I don't know what's happening. So yesterday I asked this guy to send me a picture. So when you complain that it's not clear, I asked him to send a picture, and he sent the picture, and it was quite clear. So I am very confused that what do you mean when you say it's not clear. So but it's huge, right? If I write 1 and if it looks like this, is it very difficult to understand that it is 1? That is my concern. Okay, if I write 1 and then it looks like this, then it is the first factor, then it is very difficult. Okay,
Sir,
anyways,
actually,
yeah,
it's
no,
like
I don't deny that you are finding it hard to read, but I find it I don't see a uniform solution that is. I mean, what can we do about it? That is my concern.
no. Till
Anyway,
now it was fine. The top right corner, the font size became small, so on board also it's not properly visible. That's why I said.
okay, okay, fine. So, okay, so you understood this matrix, right?
Yes, sir.
Okay, and you understood why these diagonal entries are going to be 0.
Yes, sir.
Okay, so that much is enough. So now I want to show, so these entries, so what are these, which entries are non-zero? Basically, I want to calculate that. So I generally have to calculate now this quantity. So now notice what is the property of these entries. The N naught is fixed, the LM is changing, right? So N naught LM, psi N naught L prime M prime. So this is basically all these entries. This is the general form of these entries. Now you can show that I am not doing the calculation but just writing one line. So this E dot R is basically, so E dot actually, so E dot R is basically E naught psi M0 LM R cos theta, right? R cos theta psi n naught L prime n prime, right? And that is basically E0 some normalization 0 to infinity R square R n naught L R R n naught L prime R 0 to pi d theta sin theta times the Legendre polynomial times okay. We just have to solve this integral. Okay. This integral is actually a very simple integral because this is most terms are very simple. So this term is just what you already calculated. This is just delta mm prime. This is Fourier transform of basically a Fourier transform of delta function in phi coordinate. Now this term is the interesting term. This comes from the orthogonality property of okay. So two things. It is going to be non-zero only if m is equal to m prime. That is obvious because there is only theta dependence. There is no phi dependence, right? So it has to be that. So the only way you can change a L dependence, or the only way that non-triviality can come is by L. Right? So this L and L prime plus minus 1. It's also easy to guess that why it is plus minus 1. It is because there is only one cos theta. If there would have been cos square theta, cos square cube theta, you would have seen this. So just look at the Legendre polynomial that you realize. So this whole thing with some prefactor, it is basically L to L prime plus minus 1. So the only term that will be non-zero here are those terms. Okay. And there are, the good news is there is only two such terms. Okay. In the whole big matrix, there is only two such terms, and those terms are here and here that I didn't write. 210 H1 200. The one it differs by 1. This is not true here. M and M prime are different here. Here they are again M and M prime are different. Here this is the only place where M and M prime are same and L differs by 1. Right? So this whole 4 by 4 matrix there is only two non-zero element. Everything else is 0. So it's a trivial matrix to solve. You can like very by hand also you can solve it. If you and all this happens, as I said, it's because of symmetry. Symmetry is the thing that makes your problems really trivial. Now you can ask that why did it happen? So you can also predict that this is going to happen without any calculation. It happened because your H1. Okay, let me write it here because board is not clear there. So this is again I am suggesting you to go through the calculation in your own hand and then try to ask that how can you say all these things without the calculation? The whole point of doing calculation is basically such that you can say things without calculation. Okay? So there is a famous physicist called Philip Anderson. He won Nobel Prize in 70s. He is considered as the father of condensed matter theory because he even invented the term condensed matter. Earlier it was called solid state physics. So he had this uncanny ability that he can find a solution of a problem without calculating anything. He will just sketch a picture and say this will happen, that will happen, and he will not explain anything. Right? He will just write the paper like that. Okay. Then people ask him, "How do you know?" He said, "What else can happen?" That was his answer most of the time. But the point is, although it looks from outside that he can say things without calculation, but the reason he can say things without calculation because he had done an insane amount of calculation when he was at various contexts before. So his brain developed these unusual connections which nobody else can even imagine. Right? So this is very important that you might see, okay, the solution is there in the book, the solution is done in the board, it is there in the video lecture, it is everywhere except your head, right? And until it is in your head, you cannot do anything, you cannot make a connection, you cannot foresee things, right? This is very important. So do all these calculations. Then only you can develop these unusual insights which are famous for many people who can see through things which others cannot. Okay? And that is what I can tell you. That is what makes the difference between a average scientist and great scientist. They are the main difference is their ability to see connections which are not easy to see, which anybody cannot see. And that ability doesn't come from sky. It comes from this kind of practicing a lot of calculations by thinking about them very deeply. Okay. Okay. So this property tells you the M will not change, right? Only the L can change. N is anyway not changing, right? But we are doing for a fixed N. Okay. So only, okay, this comes from the geometric symmetry of the problem, of course. That you also know a priori because you fix the one direction. Okay. And you can also say that the L selection, this is called selection rule in various other contexts, in chemistry and spectroscopy. This also comes from simple fact that x goes to minus x or whatever you can r goes to minus. So this r goes to minus r tells you, so this invariance tells you dr, this quantity is invariant under this transformation, and that tells you L minus L prime must be odd. Only when L minus L prime is odd, then in Lm some quantity, this kind of quantity R L prime can be non-zero. So you can show also that it must be also L minus L prime less equal to 1. It just says odd, it doesn't say it is plus minus 1. But for that you need something called Wigner-Eckert theorem that we didn't, that's a topic we didn't talk about. But you can go ahead and learn about it, it's not a difficult topic. Okay. I'll just write one more line just to say that what is the final answer. Okay, 5 minutes just overshot, but I'll just line the final just to complete the Stark effect. So just the answer which you will find by diagonalizing this matrix. So as I told you, this will be a matrix of this form. A non-zero entry 0 0, a non-zero here, 0 0 non-zero here, and this is minus E1 minus E1 minus E1 minus E1 and 0 0 0 0 0. This is the matrix you have to deal with. So when you solve it, and these entries, this cross is basically 200 Z210, sorry 210 Z200. Either way, it doesn't matter. This is same as 200 Z210, and Z is r cos theta. So you can calculate this. This will be minus 3e Ez a naught. So Ez is the Z e at the Z direction. Okay. So when you diagonalize, you get 4 eigenvalues, which will give you your first correction to n equal to 2 and m equal to 0. They are 0, 0. These 4 eigenvalues are 0, 0, plus minus 3e Ez. So that means your level will be L equal to 1, m equal to plus 1, 0, minus 1. This 4-fold degenerate level, they will split like this. So 2 levels, there is no splitting. These 2 will be exactly where it was, and 2 will be plus and minus, right? So you get m equal to 0, m equal to plus minus 1, and m equal to 0. You can also calculate the wave function, as you know. You can, once we have discussed this, right? So if you solve this or this, whatever you get, the 4 wave functions you get are the 4 correct 0th order wave functions, right? So they will be 1 by root 2 phi 200 phi 210 phi 211 phi 21 minus 1 1 by root 2 phi 200 plus 210. As you can see, the degeneracy is not removed here, so you have to go for another order. Okay. And as I have already shown you that for the 100 level, so up to fine structure means up to this order, this is the answer. You can go one level below, that is not fine structure, that is beyond fine structure. So similarly, you can, as I told you, that 0th order correction to 100, the first order correction is 0. So now I have to go to second order, right? So if I go to second order, you can calculate this by psi NLN E EZ psi 000 summing over NLM E100 minus ENLM, and you will find this some number you will find which is less than 0, which means the level will be pushed down, and it will be of the order EZ square with some factor. So this is called quadratic Stark effect because it is quadratic square. Okay, so that is all I wanted to tell you about Stark effect. Next class we will start with Zeeman effect. Okay, I hope everything is clear. It's all just a simple exercise of everything that you have learned till now. Okay, okay, online audience, is anybody there? I'm not
Yes,
even
sir.
answering. Oh, very good. I'm so happy. Thank you for being there. Okay, so questions now. Do you have questions? Do you at least understand that this is just a prototype of these problems you are doing all the time? This is basically this problem. What was this? Some 00A, 00B, something, that problem. Right? This is basically a prototype of this problem. That's all. There is nothing more complicated. Okay. Just the only messy part is these integrals, but if you look at it calmly, you will see there are a lot of symmetries, things are cutting each other, and it is becoming something very simple. After all this calculation, it is very satisfactory that the answer is this simple. Okay. So it tells you that if you have some spectral lines, this spectral line, this is 100, and one spectral line is for all these 4 levels, right? 200, 210, 21 minus 1, 211, this 4 line. So after, at first order, you will see as a function of E, if it is E is very small, you will see this will be shifted here at a lower side. No, this will not be shifted, this will not be shifted. This will split into 4 lines, 3 lines. Okay? This will split into 3 lines. So this is turning on electric field. Turning on electric field. Now if the electric field is even stronger, then you will see this is shifting. Okay, and you will see also these degeneracy is broken. Okay, so you are very precisely predicting experiments, and that is what happened in these cases. Like people saw this and then didn't know what is happening, and this theory is predicting all this. Okay, okay, that's all.